Probability and statistics, conditional probability. We're going to be looking at these three different types of events, comparing them, dependent, independent, and mutually exclusive, and making sure that we are aware of the difference between them. There's a lot of confusion between independent and mutually exclusive often. So two events are independent if they have no connection with one another, and the happening of one doesn't do anything to the happening of the other one. So it's two events. Tossing a coin twice. Landing on heads after tossing a coin and rolling a 5 on a 6-sided die. Notice two different events. Choosing a marble from a jar and landing on heads after tossing a coin. Selecting two cards from a pack, replacing the first before selecting the second. Notice that replacing is what makes them independent. And the probabilities are multiplied. More than a single outcome with options for each of those outcomes. Not to be confused with mutually exclusive events, which is a single event. Single event with more than one possible outcome. So I'll repeat that. Independent is more than one event, each with their outcomes, and mutually exclusive is a single event with a number of outcomes. Example, landing on heads or landing on tails after a single toss of a coin. Choosing a green or red bead in a single selection from a bottle of beads. Choosing a queen or a king from a pack of cards. And in this case, the probabilities are added. Two events are dependent when they are so connected together as that the probability of either's happening is altered by the happening of the other. Now that sounds terribly complicated, but if one event happens and therefore it affects another one, then that's dependent. A simple case is drawing two cards from a pack of cards without replacement. Once you draw the first card, if you don't replace, all the probabilities are changed now, because now there are only 51 cards to choose from. Drawing one, then another card from a pack without replacement. So selecting from two cards from a pack, and when the second card is drawn, there are fewer cards affecting the probabilities. Choosing two marbles from a jar. When the second marble is taken, there are fewer marbles left affecting the probabilities. In this case, same as with independent events, the probabilities are multiplied. But there are complications because this is conditional probability. Conditional probability of event in relation to event B in relationship to an event A is the probability that B occurs given that A has already occurred. The probability of drawing a queen from a pack of cards given that you've just drawn a king and not replaced. Notation. There it is there with the vertical stroke there. Pronounce the probability of event B given A. Let's have a look at some contingency tables. Well, a contingency table. Here's a table giving eye color and hair color and number of people. So that means there are 87 people with brown eyes and brown hair. There are 73 people with blue eyes and blonde hair. Now from this table, we can calculate probabilities. If a person is chosen at random, what's the probability that he or she will have brown hair? Now remember, probability is number of favorable outcomes over total number of outcomes. So we say, well, how many outcomes are there for brown hair? So there's brown hair, so we look all the way along and it's the total 153. Total number of outcomes, well, there it is there, 375. We add everybody together. So 153 over 375 is the probability. Hazel green eyes. Once again, hazel green. Now we're going in this direction. All those have hazel green eyes, no matter what hair color. So there's 60 of them. So 60 people have that out of 375, and there is your probability, 60 over 375. Brown hair and blue eyes. So we have to look along here and say, well, there's brown hair, there's blue eyes. So there's the intersection. That's how many people have brown hair and blue eyes is there. So number of favorable outcomes, 52, still 375 people we're choosing from. Blonde or red hair and blue eyes. So blonde or red, so anything in this here, but it has to be blue eyes, so therefore it's those two values there. So we're going to add those because there's 73 and 4 of them. So there's 77 people meeting that condition inside the blue eye column. Aha, a conditional probability. Brown hair given brown eyes. So now we already know the person has brown eyes, so we're only looking at that. We're no longer looking at that total. We're looking just at brown eyes because that's what is given. And brown hair, they're 87, so therefore 87 over 174. And there's conditional probability. Hazel green eyes, given blonde hair. So it has to be blonde hair, given blonde hair, and there's the hazel green eyes, and it's out of all the people who have blonde hair because it's given blonde hair, so it's 22 over 134. Let's have a bit of a look at tree diagrams. So we have a box containing 6 red cubes and 9 green cubes. And the 3 cubes are taken out one at a time without looking at the color. And the important thing is the cubes are not replaced. If they're replaced, then this would be independent events, but now they're dependent and it's conditional probability. So there is the first column, the first tree, the first branches. This is the first choice of the first cube. So we could choose red or green. And the probabilities are 6 out of the 15 for the red and 9 out of the 15 for the green. Now, from each of these, we can choose either red or green, red or green. But now, because this is conditional probability, and at this stage, in choosing here, 1 cube has already been taken out. You need to say, well, what is left? Well, if a red's been taken, there are 5 red left out of the 6 and still 9 green. Or if a green has been taken, there's 6 red still and 8 out of the 9 green left. And so there's your new quantities. Now we can work out the probabilities. Because to get a red, we have 5 options out of 14, a green, and 9 options out of the 14. Red here, 6 out of the 14, and green, 8 out of the 14. For the third cube, now we can have red or green for each of these options there. Let's see what's left first. Once again, we had 5 red and we chose the red, so it's 4 red and it's still 9 green. 5 red, 9 green, and we've chosen a green, so it's 5 red, 8 green. 6 red, 8 green, and we've chosen a red, so it's 5 red, 8 green. And here we've chosen a green, so it is 6 red, 7 green. There we are. So we can work out our probabilities. To get a red, we have 4 options out of the 13. Now remember, with a tree diagram, the sum of the probabilities down there must add up to 1. So that's a good check for you. Make sure they add to 1. These ones here must add to, each of these must add to 1. Each of these must add to 1. So let's find the probability that the second cube is green given the first cube was also green. There we are. Second cube, here's your second cube choice, green, but it's given that the first was green. Now notice that's a dotted line because we've been asked for the conditional probability, not the probability of getting first a green, then a green. We've been asked only for green given that a green has been chosen. So that is the probability we're going to look at. Just 8 over 14. Right, second cube probability, second cube is green given the first is a red. So there are, first red, second green. So there is your conditional probability, 9/14. Third cube is red, so here the reds in the third cube, given the first two were red. So how do we get to the third red of these four, given the first two are red? Well, there, and then on. So there is the path, and there's the probability, the conditional probability that the third cube is red given the first two red. 4/13. Third cube is red given the first two were green. Okay, so now still red, 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 but we have to get there through two greens. So therefore along this way. There we are. Green, green, and now a red. So there's your conditional probability, 6/13. Third cube is red given the first two were different colors. Now, we have mutually exclusive situation because there are two different possibilities, only one of which will work at a time. There's only one choice, and that's choosing the first two as a single choice. Choose, choose. We don't then go back and choose again, so that's mutually exclusive. And two different colors, so we could choose a red and a green that way, or we could choose a green and a red. Red, green, green, red, and finally we're choosing a red on the third one. Now notice, because these are mutually exclusive, one or the other, or we're going to add these probabilities together. So there we are there. We're going to add these two probabilities together. There we are. Independent, we just multiply the probabilities, but when they're dependent, we have to say PA, probability of A times the probability of B given A, because now A has affected it. Let's have a look at an example. 2 cards are drawn from a pack of 52 cards without replacement. We can do it with a tree diagram, but ultimately in stats, it's better to get used to the formulae, achieving the same as tree diagram. So let's do it by formula. The very last question example in this video uses both. The first for reasoning, the tree diagram, then we need to use a formula. So what's the probability that a king is drawn and then a 10? Well, because there's no replacement, we're going to have dependent events, so it's going to be conditional probability. Probability of a king and a 10 equals probability of king times probability of 10 given king. Well, there are 4 kings in the pack, 52 cards. Then choosing a 10, there's still 4 10s, but there are only 51 cards. That's why 4 over 52 times 4 over 51, that'll give us our answer. I'm not too worried about the answer. Probability that 2 queens are drawn. So probability of queen times probability of queen given queen. Now notice here there are 4 queens and 52 cards, but now that we've chosen the queen, there are only 3 left, and there are 51 cards left. What's the probability that a king and then a heart are drawn? We have to be careful here because there is a king of hearts. So we can't say probability of king times probability of heart given king. We have to divide this into mutually exclusive. We're going to have to divide it into 2 events. We're going to have to separate the king of hearts. And what we're going to do is we're going to say, well, if we're going to draw the king of hearts and then draw another heart, here's the probability. If we're not going to draw the king of hearts and then another heart, here's the probability. They'll be mutually exclusive, so we'll add them together. So, probability of A and B is probability of king of hearts times probability of heart given that we've chose the king of hearts. So, it's 1 over 52. There's only 1 king of hearts in the 52 cards. There are only 12 hearts left because I've chosen the king of hearts, and there are 51 cards left. Now here, we're not choosing the king of hearts. So probability of a king but not hearts times probability of a heart given king but not hearts. So here we are. King but not hearts, there are 3 of them, and it's out of 52. And then how many hearts left if we haven't drawn the king of hearts? Oh, well, there's still 13 hearts, and it's 51 cards. Now these are mutually exclusive, so we need to add them together. So probability of king then heart, 1 over 12 times 12 over 51 plus 3 over 52 times 13 over 51. And there is the answer, 1 over 52. Their formulae for you. There's P, probability of A in section B is probability of A times probability of B given A. That's if it's conditional probability. Though this will work even if it's independent events, because B given A, probability of B given A with independent events is just probability of B. Which means we can adjust this equation, so our probability of B given A, and we can take probability of A underneath, or we can change it and say probability of B intersection A or A intersection B is probability of B times probability of A given B, and we can do it that way around. So here's a Venn diagram. Here's each option. X is A but not B. That's the intersection. Y is B but not A. This is the number of them, and W is the outside what's left of the union of these two if we exclude that. So a few to look at. NA, remember that means number of elements in A. Right, so if we have a look, there's A, and there are the elements in A, so therefore X plus Z. Number of elements in B. Pretty straightforward, Y plus Z. Number of elements in A intersection B, which means number of elements that are on A and B, well, it's only Z. In A union B, which means number of elements in A or B, well, X, Y, and Z are all in A or B, so therefore X plus Y plus Z. This is number of elements in A complement. So number of elements outside A. Well, X and Z are inside A, therefore Y and W are outside. So Y plus W. Number of elements A complement intersection B. So everything outside A intersecting with B, and that's going to give you Y. So now, probability of A, well, that'll just be number of A over total number. Probability of B, same thing. Probability of A intersection B would just be number over total number. Probability of A union B. Probability of A complement. And probability of A complement intersection B. Pretty straightforward. You just need to work out the number first, then divide by the total number. And now, how about some conditional probabilities? Probability of A given B. Alright, so now we're given that it's B and there are Y plus Z items in it. How many are in A? Well, the answer is Z. Therefore, we'll have Z over Y plus Z. Probability of B given A. Well, in other words, it's got to be in B given that it's in A. Well, it's X plus Z in A, so we know we've got X plus Z in the total. Got to be in B, so it's going to be Z. So therefore Z over X plus Z. Probability of A given B complement. Alright, so it's got to be inside B complement, which is everything outside B, so that's X and W. But we want to know how many in A, so the answer is X. And the total in B complement, the B complement is X plus W. Probability of A complement B, well, there are Y plus Z in A complement, Y plus W in A complement. Correction. Here's probability of B is Y plus Z. So it's given that it's B, so therefore I want to know A complement given that it's B here. And the probability of A complement will be Y because that's outside A. So it's Y and it's over Y plus Z. An example, a teacher gives his class 2 tests. 25% of the class passed both tests and 42% of the class passed the first test. What percent of those who passed the first test also passed the second test? Very difficult to guess this one, but it's very straightforward if you just use the formula. And there we are. We've been asked for P of B given A. What percent of those who passed the first test also passed the second? So what's the probability that a kid in the class passed the second test given that he or she passed the first? So we know that the 25% passed the first test. So therefore P of A is 0.42. If B passed the second test, well, we're more interested in probability of B given A. So therefore that's the question mark. 25% passing both tests means that PA intersection B is 0.25. So if you have a look at the formula now, we try to find that, we know that, and we know that. So 59% of those who passed the first also passed the second. It's very interesting this to be able to calculate this sort of thing. Another example, a jar containing black and white marbles. 2 marbles are chosen without replacement. The probability of selecting a black marble and then a white marble is 0.34, so that's probability of black intersection white. The probability of choosing a black marble on the first straw is 0.47, so that's probability of black equals 0.47. What's the probability of selecting a white marble on the second draw given the first marble was black? Well, we know that probability of white then black is 0.34. That's the intersection. We know that probability of selecting a black on the first draw is 0.47. So there, probability of black, 0.47. Probability of drawing a white on the second given black on the first. So probability of white given black, we've been asked for. So we can use a formula. We can use one of these formulae here. We would say that equals probability of white then black over probability of black. So 0.34 over 0.47, and it's 72%. Probability of getting the first answer correct in a quiz is 0.6. If the first answer is correct, the probability of getting the second answer correct is again 0.6. However, if the first answer is wrong, the probability of getting the second answer reduces to 0.45. That, I think, we should summarize in a tree diagram. Often that's fairly confusing, so often a tree diagram is quite useful. There we are. If the first answer is correct, the probability of getting the second answer correct, the probability of getting the first answer is 0.6. There we have it. If the first answer is correct, the probability of getting the second answer correct is 0.6. So there we are. If the first answer is correct, probability of getting second, so there's the conditional probability. However, if the first answer is wrong, the probability of getting the second answer correct is 0.45. And so there it is there. That's the conditional probability of second answer correct given first wrong. Now we can just complete our tree diagram. Remember, add to 1, add to 1, add to 1. Now we have to find probability of first correct given second correct. P of A given B is P of A intersection B over P of B. Now the probability of A and B being correct is 0.6 times 0.6. And probability of the event where the second answer is correct, well, there are two ways the second answer is correct. There or there. So therefore, it's mutually exclusive. We have to say 0.6 times 0.6 plus 0.4 times 0.45. It's a double thing for probability of B correct. Two places. And that simplifies to 0.67.